So we'll wrap up today's lesson by talking about current division. Now, current division is really quite a lot like voltage division, with the exception that we're talking about resistors that are in parallel, and we're asking ourselves how much of a total current is passing through each of the two resistors, rather than resistors in series and asking how much of a total voltage appears across each of them. So you can see here in figure 6, resistors in parallel showing a total amount of current. We want to find out what is I1, the current that is passing through R1. We want to find out what is I2, the current that is passing through R2. Well, the equations are quite similar, and if you just glance at those two equations, equation 3 and equation 4 look an awful lot like the equations for voltage division. But there's one really important difference here. Yes, there is the total current being multiplied by a fraction. That makes good sense. And the sum of the two resistors is in the denominator. But the big difference is that if you want to know the current in branch number 1, the numerator needs to be the resistance in branch number 2. That's quite different. If I flash back to voltage division, so up here in voltage division, notice that V1 had R1 in the numerator. V2 had R2 in the numerator. But down here for current division, I1 has R2 in the numerator, and I2 has R1 in the numerator. You might ask yourself, why is that? Remember that phrase that something follows the path of least resistance? Well, you know what follows the path of least resistance literally is current. Current will go through a path if it has lower resistance. And if it has higher resistance, it will tend not to go through that path. Now, I'm not talking about it's 100% of it's going to go through one path or the other, sort of like the highways that feed into a city. If they can sense that there's a lot of current going in one path, maybe some of it will go in the other. So even if one path is quite a lot harder than the other path, a few electrons will go along that path. A little bit of current will go that way. It's just definitely more of the current will go along the easier path. So what does that mean for our circuit here? Well, if R2 is much, much larger than R1, so as R2 increases, certainly that's going to be the harder path. And then R1 will become the path of least resistance. So I1 will increase as R2 increases. And that's exactly what we see in equation 3. I1 will increase as R2 increases. All else being the same, if R2 increases, I1 will increase. Similarly, if R1 increases, then I2 will increase. So as R1 increases, I2 will increase. So there is one difference here, and that is that which variable appears in the numerator. But if you just think about it in terms of that path of least resistance, on the one hand, I've got this nice, big, smooth pipe that water can flow through very easily. On the other hand, I've got this really old pipe that's rough, and the diameter is not very big, and it's really hard for water to flow through there. If you think about it in that way, you're going to find that R1 and R2 appear in the right places in these equations. One last thing to think about when you're talking about either voltage division or current division, if R1 equals R2, then the voltage is going to be split in half for voltage division, and the current is going to be split in half for current division. That really makes sense. If R1 and R2 are equivalent paths, then it makes good sense that the current is going to go 50% to the left and 50% to the right. That's just a special case. Now let's look at one example here with some numbers attached to it. So I have here a 9 amp current source that's being divided between a 10 ohm path and a 5 ohm path. Now before we even look at the numbers to the right, we know that I1 plus I2 has to add up to 9 amps. Kirchhoff's current law at this top node would say that 9 amps flows in, I1 flows out, I2 flows out, I1 plus I2 has to add up to 9. Furthermore, I can see that the 10 ohm path, that's going to be the higher resistance. So I1 will be lower than I2, probably maybe by a factor of 2 or 3. And so you can see here that I2 will be the higher current because it's going through the lower resistor, again, probably by a factor of about 2 or 3. So now we can plug the numbers in. IS is 9 amps, R2 is 5 ohms, R1 is 10 ohms. When we plug this all into our calculator or do it in our head, we find that I1 is 3 amps and I2 is 6 amps. Great. 3 amps plus 6 amps adds up to 9 amps, so that's correct. And as we saw, I1 should be less than I2, probably by a factor of 2 or 3. In this case, it worked out to be a factor of 2. So current division allows us to quickly and easily calculate what fraction of the current and what is the total amount of current that flows through each of two resistors that are in parallel. So now you have enough information to go back and, that says voltage division, but you should go back and solve the current division example problem, and then you'll be ready to come to class tomorrow.